Real-world application of AP sums. Welcome, everyone. Up until now, in our previous lessons, we have spent a lot of time focusing on the theory behind arithmetic progressions, specifically, how we derive the formulas and how to performing the basic calculations for the sum of an AP. But today, we are moving beyond just the formulas. The real power and true utility of these mathematical tools lie in their ability to solve practical, real-world problems. Think about it. Whether you are trying to calculate your total savings accumulated over several years, predicting how much a factory's industrial production will grow, or even determining the total number of seats in a large stadium, the sum of an arithmetic progression provides us with a highly efficient mathematical framework to find those answers accurately. In the following slides, I will show you exactly how to apply these theories to these types of real-life scenarios. Solving real-world problems using AP. Now that we've established that the formulas we learned in our previous lesson aren't just theoretical, let's look at how we actually apply them. To solve real-world problems using arithmetic progression, we aren't just going to jump straight into calculations. Instead, we are going to follow a structured, three-step process to ensure we don't get lost in the text. The very first and most critical step is what I call translating word problems into AP notation. Think of this as decoding the story. When you read a word problem, your goal is to strip away the fluff and translate the English text into mathematical symbols. You need to carefully identify which piece of information corresponds to which variable in our AP formulas. Let's break down exactly what you should be looking for. First, look for the first term, which we denote as a. This is your starting point. You'll find this by looking for words like the starting value, the initial amount, or the value during the first time period. For example, a sentence like, "In the first month the factory produced," tells you exactly what A is. Next, identify the common difference, represented by the letter T. This is the rate of change. You are looking for phrases that indicate a constant shift, such as increases by a constant amount, a fixed monthly increment, or even a decrease by a steady rate. If the value is dropping, remember that D will be negative. Then we have the number of terms, which we call N. This represents the total duration or the total number of items you are summing up. Be very careful here. If a problem mentions a duration of 2 years, but the production is measured monthly, you must convert that to 24 months so that N equals 24. Fourth, look for the nth term, written as a sub n. This refers to the value at one specific, particular position in the sequence. For instance, if the problem asks about the production in the 10th month, it is asking you for a sub 10. Finally, identify the sum of n terms, which we denote as S sub n. This is different from a single term. This refers to the total accumulated value over the entire period. If the question asks for the total production for the whole year, you are looking for the sum, not just a single month's value. Mastering this translation step is the foundation. Once you've decoded the variables, the next step, which we will cover in the next slide, is setting up the equations to find any missing pieces. Setting up a system of linear equations. Now, moving on to slide 3. Up until now, we have mostly dealt with problems where the starting value and the constant increase were handed to us on a silver platter. However, as we step into more advanced territory, you'll find that the first term, which we call a, and the common difference, a lowercase d, are often hidden from you. Instead of being given those starting values directly, the problem might only give you 2 different terms from somewhere in the middle of the sequence. When this happens, you can't jump straight to the sum formula like we discussed in the previous slide. Instead, you need to use the general term formula. That is, a sub n equals a plus the quantity n minus 1, all multiplied by d, to build what we call a system of linear equations. Let me walk you through the logical process using an example. Suppose a problem tells you that the third term is x and the 7th term is y. First, you will write an equation for that third term. Since n is 3, n minus 1 is 2, so your equation becomes a plus 2d equals x. Next, you do the same for the 7th term. Here, n is 7, so n minus 1 is 6, giving you a plus 6d equals y. Now you have two equations with the same two unknowns. To solve this, you should subtract the first equation from the second equation. This is a great trick because the terms will cancel each other out, leaving you with just d to solve for. Once you have successfully found the value of d, your final step is to substitute that value back into either of your original equations. This will allow you to isolate and find your starting term. Once you have both and d, you'll be fully equipped to use the sum formulas we are about to see in the next slide. Calculating the final result. Now that we have discussed how to set up a system of equations to find our missing variables, let's look at what we actually do with them. Once you have successfully solved for the first term, which we call and the common difference, d, you have essentially unlocked the key to the entire sequence. With these two values in hand, you can find any required value the problem asks for. There are two main types of questions you will encounter. First, if the problem asks you to find a specific future value, for example, the production amount in exactly the 10th month, you will use the general term formula. That is, a sub n equals a plus the quantity n minus 1 multiplied by d. On the other hand, if the problem asks for the total accumulated sum, meaning the total amount produced or saved over the entire duration, you will use the sum formula. In this case, S sub n equals n divided by 2, multiplied by the quantity 2 plus the quantity n minus 1 multiplied by d. Keep these two formulas in mind, because in the next slide, we are going to put them both to work in a comprehensive, real-world example. Comprehensive, real-world example. Let's look at this scenario. Imagine a factory that increases its smartphone production every single month. We are given two specific pieces of data. In the 4th month, they produced 640 units, and by the 9th month, that number grew to 890 units. Our objective is to find the total number of smartphones produced over the entire first year, which is a period of 12 months. Step 1, translation. We need to decode this word problem into our AP notation. From the text, we can see that the production in the 4th month, which we call a sub 4, equals 640. The production in the 9th month, or a sub 9, equals 890. Since we are looking at a full year of monthly production, our number of terms, n, is 12. Our ultimate goal is to find the total accumulated sum, which we denote as S sub 12. Step 2, setting up the system of equations. As we saw in the previous slide, we don't have the first term or the common difference yet. So, using our general term formula, where a sub n equals a plus n minus 1 times d, we can create two equations. For the 4th month, where n is 4, we get a plus 3d equals 640. This is our first equation. For the 9th month, where n is 9, we get a plus 8d equals 890. This is our second equation. Step 3, solving for d to find the common difference, we will use the elimination method by subtracting the first equation from the second. When we subtract a plus 3d from a plus 8d, the terms cancel out, leaving us with 5d. On the right side, 890 minus 640 gives us 250. So 5d equals 250. Dividing both sides by 5, we find that d equals 50. This means production increases by 50 units every month. Step 4, solving for a. Now that we know d is 50, we can substitute this back into our first equation to find the starting value. We have a plus 3 times 50 equals 640. Since 3 times 50 is 150, the equation becomes a plus 150 equals 640. Subtracting 150 from both sides, we find that it equals 490. So, the factory started with 490 units in the first month. Step 5, calculating the final result. Now we have all our variables. A is 490, d is 50, and n is 12. We can now use the sum formula, which is S sub n equals n divided by 2, multiplied by the quantity 2a plus n minus 1, times d. Plugging in our values, we get S sub 12 equals 12 divided by 2, multiplied by the quantity 2 times 490, plus 12 minus 1, times 50. Simplifying inside the brackets, 12 divided by 2 is 6. Inside the brackets, 2 times 490 is 980, and 11 times 50 is 550. Adding 980 and 550 gives us 1530. Finally, multiplying 6 by 1530, we arrive at our final answer. The total number of smartphones produced in the first year is 9,180 units. Now that we have discussed the theory and the strategy for setting up equations, let's put everything we've learned into practice with a comprehensive example. To solve this, we will follow the structured process I mentioned in the previous slides. As we move to the next slide, I want you to pay close attention to the common pitfalls that might have occurred during this calculation, such as confusing the term value with the total sum. Common mistakes to avoid. First, one of the most frequent errors is confusing the nth term, denoted as a sub n, with the sum of n terms. Denoted as s sub n, it is very easy to accidentally use the summation formula when the question is simply asking for the value of a specific term, or vice versa. To avoid this, I want you to pause and ask yourself a critical question. Am I looking for a single value at a specific point in time, which would be a sub n, or am I looking for a total accumulation over a period, which would be s sub n? Second, pay close attention to your value for n. A common mistake is using an empty number of terms due to mismatched time units. For instance, if a word problem mentions a duration of 2 years, but the growth or change is happening on a monthly basis, you cannot simply use 2 for n, you must convert that time into months, meaning n must be 24, not 2. Always ensure your n matches the frequency of the common difference. Third, watch out for the n-1 error. When you are using the formula for the nth term or the sum, it is very easy to forget to subtract 1 from n inside the brackets. Remember, for the 12th term, the coefficient of d is actually 11, not 12. This small oversight can throw off your entire calculation. Finally, be extremely careful with sign errors regarding the common difference. If the problem describes a scenario where production or savings are decreasing, you must remember that d must be a negative value. Make sure that negative sign is carried through every single step of your algebraic manipulation to ensure your final result is accurate. Now, before we wrap up today's lesson with our final summary, I want to pause and discuss some common pitfalls. Even if you understand the formulas, these specific mistakes can lead to incorrect answers in an exam setting. Keep these traps in mind, and you will find much more success in solving these complex applications. Key takeaways. First, always start by identifying your knowns. Before you even touch your calculator, list out your variables. Find your first term, your common difference, the number of terms, the nth term, and the sum of n terms. Writing these down clearly prevents you from getting lost in the word problem. Second, remember the strategy for using a system of equations. As we saw in our smartphone production example, if the problem doesn't give you the starting value or the common difference directly, don't panic. Use the 2 terms provided to create 2 linear equations and solve them to find your missing variables. Third, follow a logical flow. Success in these problems comes from a structured approach. First, translate the text into mathematical notation. Second, solve for your unknown variables. And finally, apply the correct formula to find your answer. Lastly, always keep an eye on the context. Make sure your units are consistent. If your common difference is monthly, then your number of terms must also be expressed in months. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid foundation for tackling these problems in your exams. If you follow these steps and avoid the common pitfalls we discussed earlier, you'll find that applying arithmetic progressions to the real world becomes much more manageable. Great job today!